Okay, so in this last section, in the equilibrium chapter, we're going to take a look at a principle. We're going to take a look at it qualitatively, meaning we're just going to be examining it from the purpose of describing the changes, not actually doing any calculations or quantitative look at it. And this principle applies to systems that are at equilibrium. So this is the first thing that we need to consider. And this principle is called Le Chatelier's principle, so named after a person, as you can imagine. And again, this affects systems that are at equilibrium, right? So what this principle states very simply is that when you have a system at equilibrium and you disturb or perturb it, or you apply a stress to the system at equilibrium, that system will respond in such a way to minimize the effect of that stress. And as a result of that, it is going to re-establish a new equilibrium. Okay, so as an analogy that we use at the beginning, if you think about being on a treadmill, okay, so you hop on the treadmill, first of all, you set it to whatever, 5 miles an hour, and then the treadmill starts to move, or the tread on it starts to move, and then you move, or you run at the same rate of speed in the other direction, 5 miles an hour. So you establish an equilibrium. Well, if somebody disturbs that equilibrium, let's say increase the speed of the treadmill to maybe 6 or 7 miles an hour, you have to respond in such a way to minimize the effect of that disturbance. And that response that you make is to increase your speed as well, right? And as a result, you establish a new equilibrium with new speeds in the forward and the reverse direction. So it's the same idea applied on a micro scale to chemical reactions. We're going to start off with the system at equilibrium, and then we're going to stress it. We're going to apply a stress to the system, and that stress can be any of the following. So we can add a reactant or a product. So just remember now, when we deal with our chemical reactions by default, we have reactants on the left and products on the right side. Even though this is a reversible process, we're still going left to right by convention. So we can add stuff to the left side, right? So the reactant side here is the left side. The product side is the right side. We could also add product to this as well. Okay, and how will the system respond? Well, we're going to take a look at it. We can remove something from the left side or something from the right side. How will the system respond in such as a result of such a stress? We can also change the volume of the system. Okay, we may change the container from a large container to a small container, or from small container to a large container. And that will then change, especially now in terms of gases, it'll change the concentration or the partial pressure of the reactants and products, because gases are the physical states that are most affected by changes in volume. And then finally, we can change the temperature, right? How will that affect the equilibrium? How will it shift in response to such a stress? So let's take a look at adding or removing something from a system at equilibrium. So we have here a reaction we've seen before. By the way, this is called the Haber process for the manufacture of ammonia. So N2 plus H2 to give 2H NH3. Reversible process, we have our balance equation, and then we're told at equilibrium, we have our equilibrium concentrations. So remember, we can write our equilibrium constant expression. So we have our product raised to its stoichiometric coefficient times the reactant raised to their coefficients as well. We're going to take our equilibrium concentrations. We're going to substitute it into our expression. We can solve for Kc, which ends up being 0.297, right? So this is at equilibrium. That's our Kc value. Now the stress that we can apply to this is we can add more of one of the reactants. That this is one type of stress that we can apply to the system. And the reactant that we're adding is a little bit more N2. So now our N2 concentration is more than it was previously. Now it's 3.51 molar. These, the H2 is the same to start with, and then the NH3 is the same to start with. So if we plug these numbers back now into our reaction quotient expression, and we solve for the QC, we see that the QC now ends up being 0.173. So this, by adding more reactant, what we find is we end up with a reaction quotient now that is less than our equilibrium constant. And as we saw previously, if the reaction quotient is less than that, the system then will move, or the equilibrium will shift to the product side or to the right side, right? And that is now as a direct response to that stress that we placed on the system. So we can take that and we can apply it to some general examples also, but let's take a look here specifically and see. We can plot the concentrations as a function of time. So originally here we have a concentrations of our equilibrium concentrations of the N2, the H2 and the NH3. And then at this point right here, we've introduced the stress, right? And the stress to the system is we added N2. Obviously, the concentration of the N2 goes up. And then what happens as a result, if we increase some of the N2, well, in order to shift to the right side, right, we have to use up some of the H2 to convert it to ammonia. So as a result, the concentration then, as we use up the H2, the concentration of the H2 is going to decrease as it's being used up. And that's exactly what we see here in the green line. At this point, the green line actually starts to decrease. And as we use up the H2, guess what? We make more of the NH3 as the reaction shifts to the right. And as a result, the concentration of the NH3 starts to increase. And then what we've done is we've established at some point, maybe right about here, right, we've established a new equilibrium. Where again, at that point onwards, the rate of the forward and the rate of the reverse reactions are going to be equal to each other. Okay, so without doing too much too many calculations, we can just qualitatively take a look at the changes that are happening as we place a stress on the system. So we can generalize this and we can say the following. If we add, so this is going to be our stress, and this is going to be the shift that accompanies that stress. So the stress here that we're applying, we're generalizing from the first one, is if we add a reactant, the equilibrium is going to shift to the right or to the product side. And then alternatively, okay, if we add a product, you can probably imagine what's going to happen. So if we add something to the right side of the equation, the equilibrium is going to shift to the other side, to the left side. So in other words, when you have a system at equilibrium and you add something to one side, the equilibrium shifts to the other side, right? That's the generalization we can make. Now, in addition to adding reactant or products, we can also remove reactants or products, and then the opposite is going to happen. So if we remove a reactant, so for example, if we took away some of the NH2, so we reduced its concentration, well, then the equilibrium is going to shift to replace some of that N2 that we removed. And in order to replace it, we need to make more of it, then the reaction has to shift this way. So if we remove a reactant, the equilibrium is actually going to shift in that direction. The reactant's on the left side, equilibrium is going to shift to the left. So it's like we made a hole, and when we remove something and the equilibrium shifts to fill that hole. Similarly, if we remove a product, so the product's on the right side, now we have a hole on the right side, the equilibrium is going to shift to fill that hole on the right side. It's going to shift to the right. And that's the product side. So the generalization there is wherever you remove, if you have a system at equilibrium and you remove something from one side of that reaction, the equilibrium shifts to that side. Next set of stresses that we can place on a system at equilibrium would be changes to the volume and then consequently changes to the pressure of a system. And here we're going to be looking now specifically at equilibrium systems that contain gases. Okay, and that's because gases are things that occupy really large volumes in the first place, and as a result, they're going to exert a pressure. So generally, what we're going to see, we'll talk about the general rule now, and we'll look at some specific examples. When the volume is decreased, okay, so we go from a big volume to a small volume, the equilibrium shifts towards the side with a smaller number of moles of a gas. Okay, so if volume decreases, equilibrium shifts to the side with fewer moles of gas. So we can have heterogeneous equilibria where we have a mixture of phases, but we're just going to be focusing on the gases here again because gases occupy larger volumes compared to liquids and solids and aqueous solutions, and they're also going to exert more pressure. So if we have here an example of N2O4 reversible reaction to form NO2, we've seen this reaction before. Okay, at equilibrium, we have our concentrations. We can calculate our Kc, fairly small value. Equilibrium is going to lie here to the left side. If we decrease the volume, right, what happens then is the concentrations are initially going to double if we decrease the volume by a half, because now the concentration is moles over volume, right? So if the volume goes down, the concentrations are going to go up. And then what we're going to see if we plug those numbers into now our QC expression, okay, the QC ends up being a slightly larger value than what was previously. So our QC now is going to be greater than Kc. Equilibrium is going to shift to the left side as a result of that, right? So decreasing a volume leads to the shift, to a shift in equilibrium to the side with a fewer number of moles, right? So here we have two moles on the right side, 2 moles of gas on the right, and then on the left side we have 1 mole of gas. So that's why decreasing the volume forces this to move to the left, where there are fewer number of moles of the gas, the N2O4 too. I'm sorry, N2O4 in this case. So we could also just complete this discussion by talking about the opposite. Okay, so if the volume is increased, then the opposite would happen. So the equilibrium will shift to the side with the greater moles of gas. With greater moles of, again, the more gas you have, the more gases you have, not necessarily the more gas that you have. The more gases there are, the more moles of gases there are in the equilibrium system. That's the side that the equilibrium is going to shift if you increase the volume. Okay, let's take a look at maybe 1 or 2 examples here. So we have, let's take a look at the second one. Okay, so this is our equilibrium system, and then we're looking in which direction will the equilibrium shift when the volume of the reaction vessel is decreased. So volume is going down, okay, and according to the principle we just talked about, equilibrium shifts towards the side with the fewer number of moles of gas. So in this example, okay, on the right side of this equation, we have 2 moles of the SO2 gas, and on the left side, we have 3 moles of O2 gas. We're not concerned with the solids. Okay, so if We have fewer number of moles of gas on the right side, and we decrease the volume. Volume shifts, so the equilibrium shifts to the side. With the fewer number of moles of gas, equilibrium is going to shift to the right side or to the product side. So we've seen so far changes in concentrations of reactants and products and how they can lead to a shift in the equilibrium. We've seen changes in the volume and how that influences the change or the shift in equilibrium as well. Now we're going to take a look at changes in temperature. And one thing to keep in mind is when we change the volume and we change the concentration, they actually don't change the value of the equilibrium constant, right? So Kc is the same in the previous examples that we've looked at. When we start changing the temperature, what we actually do is we're now going to affect the value of the equilibrium constant. So Kc is actually temperature dependent, right? And all of the examples we've looked at so far, when we've calculated a Kc value, we've always specified at what temperature is calculated. So what we're going to take a look at now is how changing the temperature can influence the direction of an equilibrium. And the thing that you want to keep in mind here when we look at changes in temperature is we need to, first of all, figure out, or we need to know whether the reaction is an endothermic reaction or whether it is an exothermic reaction, right? And we saw this way back in the thermochemistry from Gen Chem 1. You'll say recall thermochem. Okay, endothermic reactions are reactions that absorb heat. Okay, whereas exothermic are ones that release heat. So as a result, what we can do is we can actually make our life a lot easier with these, and we can think of the heat itself as either a reactant or a product, right? So if you remember also for endothermic reactions, our delta H, our change in enthalpy, was a positive value because we're gaining heat, whereas for an exothermic reaction, our delta H, because heat's being released, was a negative value, right? So these are things that you can look at. If you're given the information for reaction, we can look at the delta H values and we can say really quickly whether we have an endo versus an exothermic reaction. And then what we can do is we can treat that heat as either a reactant or a product. And then we apply the same principle as we did for changes in concentration. Okay, so for an endothermic reaction, let's take a look at the first example. So for an endothermic reaction, we can think of heat as a reactant. So we can write it here on the left side. Write the word heat in there, it's easier to interpret now. Okay, if we add some of the stuff on the left, which is where the heat is in an endothermic reaction, equilibrium has to shift towards the other side, right? And if it shifts to the right, the Kc value is going to increase because we are now increasing the amount of stuff on the right side of the equation that is in the numerator. Remember, our Kc is product over reactants. Okay, and then conversely, if we remove heat, if we cool this system down, we take something away from one side, equilibrium shifts towards that side. So now the products get used up, products concentration decrease. This numerator here is a smaller value. The denominator becomes a bigger value. This makes the Kc value go down, and as a result, Kc is going to decrease. Okay, so that's the way that we're going to interpret, or we're going to evaluate the changes or the shift in the equilibrium and the consequent change in the Kc value. We're going to treat heat as either a reactant for an endothermic process, and then the opposite would be true. If it's an exothermic process, okay, then heat is going to be a product on the right side. You can write the word heat in there to simplify things. So now, if we add heat, if we add something to the right side, remember now, equilibrium shifts in the other direction. So as a result, add heat to an exothermic process, we force the equilibrium to the left, we increase the amount of reactants, so the denominator increases, the products get used up, so as a result, the Kc value is going to decrease. And then on the opposite side of this is if we remove heat, if we take away heat, if we cool this down, the system responds to produce more heat, which is going to shift to the right. And as a result, the Kc value is going to increase as a result. Okay, so it's very, very simple to interpret changes in temperature if we know whether the reaction is exo or whether it's endothermic. We can also monitor changes or the shift in the equilibrium as a consequence of temperature changes, especially um, if our system has colored species in it. Okay, so the example that's shown here, we have this species that has a blue color on the left side, on the reactant side, and then this other hydrated species that has a pink color on the right. And this process, right, releases heat. So this is exothermic. And we can actually see the changes in color as we do certain things to it. So originally, this is our original color for this system at equilibrium. If we apply heat to it, okay, now we add heat, we add something to the right side, equilibrium shifts to the left, and as a result, the blue color is going to dominate. Now, if we cool this down, this is ice in here, by the way. If we cooling down something means we're removing heat, so we take something away from the right, equilibrium shifts towards that side. This side has a pink color, and that's what we actually see. Okay, so monitoring the color change can tell us by extension in which direction the equilibrium is shifting. Okay, so that's changes in temperature. We need to know whether the reactions are endo or exothermic. All right, and then the last thing we'll just address really quickly here is the use or the presence of catalysts. Okay, so we saw catalysts back in the kinetics, chemical kinetics section, and we saw that catalysts are things that speed up the rate of a reaction or increase the rate, sorry, increase the rate of a reaction or increase the speed. However, a catalyst does not affect the equilibrium. It does not affect the position of the equilibrium. Okay, it doesn't force it to go to the left or to the right. That's not the function of a catalyst. Instead, what a catalyst does is it allows the equilibrium to be established much quicker than if we didn't have a catalyst present, right? So catalysts speed up reactions. They allow us to get to equilibrium much quicker. They do not force the equilibrium in any net direction to the left or to the right. Okay, so that's a common misconception about catalysts, that they affect the equilibrium. No, they just allow us to get to equilibrium much more quickly.